This is joint work with Zhiguo Fu, Kurt Gersmeyer, and Michael Kowalczyk. And as Anna introduced, that this is aimed at deriving a trichotomy, which means that a three-way partition of the problem universe for, in particular, the K-regular case of spin systems where the functions sit on the edges, but they do not necessarily have to be symmetric. And I'll get a little more technical later, but basically, I think perhaps in keeping with the spirit of this conference, I'd like to show you a puzzle where Anna already mentioned, and I think any high school student would find it interesting. So the main theorem of the paper is a classification where we'll talk about the spin systems that I'll define in a bit more on K-regular graphs. And you have functions that are sitting on edges that are not necessarily symmetric, but they're binary functions. So basically, you have spins on vertices going up and down. So you have up, 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 down, down, up, down, down. You have 4 values. And the edge function gives you one of those 4 values depending on the assignments. And you are looking at what's called the partition function, which is sum of all possible assignments of 2 to the number vertex assignments. And for particular assignments, you'll multiply the edge function. That's what's called the weight of this particular assignment. And that's called the partition function. I'll define it a bit more. But basically, we're going to try to classify such computation, which by definition is exponential. But in some cases, it could be polynomial. And then we'll bring in a third case where it is generally hard, but for planar graphs, it's polynomial time solvable using what's called the Castellan's algorithm. OK, so now end with complexity theory. I should say that the statement sort of says that I have 3 categories, that it's polynomial time computable in general, or Sharpe hard, but polynomial time computable on planar, and Sharpe hard even on planar, and nothing in between. So this is the trichotomy. You classify everything. OK, so this comes out of the big classification program on counting problems, where I will, if I have time toward the end, I'll mention a few words. This is one special theorem. And for this talk, I will just focus on this interesting connection with number theory, where it goes into one of the proof of this, actually both for these 2 parts. And it's sort of, I won't actually give you even an overview of the proof of this whole thing, but this particular lemma, I think, would be sufficiently interesting in of itself, and hopefully you will find it so. So here's the question. You have 2 angles strictly between 0 and 90 degrees. And so therefore, say the cotangent value, of course, is anti-monotonic. So it is between 0 and then infinity. They're distinct. And suppose that you know for a fact that the one is a multiple of the other by a factor of 2. OK, so you know that they are rationally connected somehow. And now, is it still possible that both these 2 angles are rational multiples of pi? So that's the question. So what has this got to do with complexity theory, right? OK, so this is like a pure, trigonometry or something. Now, turns out these multiples of pi's correspond to roots of unity in the angle. And they come into the proof of complexity theory because we want to have certain reductions that work, that by proving that a certain van der Waals systems don't vanish. And in order to say the van der Waals systems don't vanish, we have to say the eigenvalues somehow are distinct. And it turns out that we have constructions that give rise to these eigenvalue ratios. And we do know that they already satisfy a factor of 2 difference. And so therefore, one of them would not be a roots of unity if this was not always the case. OK, so this is how the connection would go. I'll explain. So the theorem for this lemma says that in this case, it cannot be both rational multiples of pi. OK, and this is one of the key results, although it's still a small part of the proof. So proving this part is the number theory part, which is probably 1/4 of the paper, and then the rest is 15 pages. Okay, so let me formally define the spin system. So you have a k-regular graph. You have a binary constraint function sitting on the edges. And depending on the assignment on the vertices of 0, 1, up and down, it will give you a value. And in particular, this value could be positive as well as negative, so there are cancellations. And when there are no cancellations, these are sort of non-negative value, the partition functions. The complexity is somewhat easier to analyze, but when there are cancellations, then there are fantastic algorithms. Think of determinants. When there are cancellations, then certain unreasonable polynomial time algorithms appear, so to speak. And nevertheless, you are looking at this partition function, which is the sum of all possible spin assignments for every vertex, so that 2 to the n assignments here. And for every particular assignment, you are multiplying the value. So if this value was 0, 1, then this multiplication can be like a conjunction, right? They want everybody's to be on. But in general, it could have even negative things. So there are weights, and you sum them all up. Another way to express this is what's called the Holland framework. I won't have much time to talk about it, although the actual proof in the paper sort of goes through this framework. Okay, so this is the definition. And the trichotomy we want to show is the classification of the computational complexity of this, where the input size is G, F is fixed. And depending on what F, there are infinite many Fs, but for what F is it computable in polynomial time, for what F it is not. Okay, yes, Bobby?
You're taking the product over directed edges of the...
Yeah. So if the function is not symmetric, then we are basically saying there are directions, if you will. So the assignment of the function tells you, this is my first vertex, this is my second vertex. So in effect, it tells me there's a direction on the edge.
So k-regular means in degree plus out degree?
Yeah, in this case. Okay, so here are 3 particular examples. So if you take this particular function, and by this function, I mean you just tabulate your function value into a matrix of 2 by 2 in this particular case. So if both edges coming 0, both vertices coming 0, 0, 0, 1, 1, 0, 1, 1, you get these 4 values, okay? And you can just convince yourself this is talking about independence set. Okay, this is an undirected graph because it's a symmetric matrix, right? It basically, the product where these values will participate will be either 0 or 1. And it will be 1 if and only if none of the edge gives me a 0, 0, which means none of the edge have both vertices are chosen to be up. Okay, so this is independence set. And in this case, it's the anti-chain. In this case, it's the even-induced subgraphs. And there are so the negative cancellations happens to come in. And this is the Adama matrix. So it turns out that, for example, in this case, it's actually polynomial time computable. And for the others, it is generally sharply hard. So the classification theorem is basically saying, give me an arbitrary F for what happens. OK? All right. So the statement of the trichotomy uses some existing theory to describe this classes of functions, which I call the product types and the affine types and match gates. I really don't have time to describe all of them in detail, but they correspond to what's tractable. And roughly speaking, for example, the affine type correspond to a certain quantum-like gates that they call the stabilizer gates. Okay? And the match gates are what was introduced by Les Valian, and they sort of correspond to perfect matchings. And this is the interesting case where you actually can have the problems generally sharply hard, but on planar graphs, it's transformable to a polynomial time by computation by the Castellan's algorithm. And what is somewhat further interesting is that the theorem says that you give me this partition function to be considered, and I tell you these are the possibilities. And for the category of the problems for which it is generally sharply hard, but polynomial time solvable on planar graphs, there is one single universal algorithm. And this is, I think, is somewhat quite unique in if you think about, like, if you think in terms of like dynamic programming, you say, oh, I can classify, formally speaking, this is the type of problems that are solvable in polynomial time by dynamic programming, and that's the only one, okay? If it's ever solvable in polynomial time, then it's solvable by dynamic programming. I don't think we have even sort of a formalized way of say such things. So when we say what is solvable by dynamic programming, it's not quite clear what that means precisely. But here, there's actually a theorem that you can prove. Oh, my battery died? Oh. Okay. Okay, so let's see. So as I mentioned that in the proof of the complexity classification theorem, we will end up having to deal with Vandermonde systems. And there we wish to argue that somehow the Vandermonde system is a full rank. And what will control the Vandermonde system to be a full rank is the fact that the corresponding sort of values to which you're going to raise to a certain power are all distinct. And these values, turns out, in this proof will be ratios of eigenvalues. Okay? So I have certain constructions for which I will produce, and that can be characterized by some sort of 2x2 matrices. I'll show you some examples. And then I will have eigenvalues for this 2x2 matrix. And then there's a ratio of the two eigenvalues. And if the eigenvalue ratio is a root of unity, then this construction will sort of repeat after some n times. And this will not be able to produce an arbitrarily large full-ranked Vandermonde matrix. Okay, so this is, I'm not getting into all the details, but you get a flavor of this. Okay? So what I like is to have constructions where the ratio of the eigenvalues of these constructions are not roots of unity. And now you can see the connection to the cotangent question, that I wish to have these quantities that control eventually the Vandermonde system to which I proved the success of the reduction. I wish to prove that these quantities, which are roots of unity, which are ratios of the two eigenvalues that are not roots of unity. Okay. Now, in previous papers, we have these issues of trying to show constructions whose ratios are not roots of unity by arguing that somehow they have different norm. And if they are different norm, then the ratio is not roots of unity. That's a sufficient condition. But it turns out in this case, there are some tricky cases where we couldn't do that. However, we, by some miraculous coincidence, perhaps, we have two constructions. And don't ask me how you get to these matrices. These are somewhat a simplified cartoonish representation of them. But nevertheless, I got two constructions. And the key part of the two constructions will give me these two sort of matrix representations about the relevant feature. And we will then be talking about their eigenvalues. And they will have two eigenvalues for the first construction, two eigenvalues for the second construction. And you'll have two ratios respectively. And what you wish to say is the ratio is not a root of unity. And then this will lead to a success of the Vandermonde system non-vanishing that I'm not showing here. Okay? And yet, I actually could not say that they are not roots of unity, or not norm 1 for one thing. Nevertheless, for the parameter settings of the given f function, that's a constraint function, here is simplified to the x and y, a, b, then I can argue that the ratio of the eigenvalues would have the following property, that they would correspond to the angles, I guess what's called the argument, the complex argument, where the cotangent of the argument is a factor of 2 from one to the other construction. So I have two constructions. I've got two matrices. These two matrices give me two pairs of eigenvalues. Their ratio is going to give me this A over B versus A over 2B. The cotangent of the angle of the ratio. Okay, you get it. So therefore, this goes back to my original question that I have two eigenvalues whose cotangent values are factor of 2 from one another. And is it possible that both are still roots of unity? Because if they are both still roots of unity, then both construction failed. What I want to say is that it is not possible that both of them are roots of unity. Okay? So by now, have you figured out my original puzzle that you have two angles, phi and psi, where cotangent is 2 times the other? Is it possible that both of them can be rational multiples of pi? And so the theorem says that in general, if one is a rational multiple of the other, then it is not possible that both are rational multiples of pi, the angle. If the cotangent values are rationally related, then it is not possible that the angles are both rational multiples of pi. with one actual exception, which is, you see, pi over 3 and pi over 6. They are actually factors 3 from each other, right? The cotangent. Okay, so it's not totally obvious that this claim that it must not be both rational multiples of pi, but in fact, this is the only exception. And so the factor of 2 was not one of those exceptions, and therefore we succeed in our dichotomy proof. Okay? So there's, yeah?
Can they be rational multiples of each other?
That is possible. Yeah, that's possible. It's tricky. So this type of questions actually had quite a bit of a history. Siegel, this is called Ludwig Siegel, proved that for cotangent values with the same denominator n, but for k that are between 1 and half n, but of course relatively prime to n, because then they would correspond to sort of a primitive roots of unity of order n. And these cotangent values are actually rationally independent. Okay, so that's a Siegel theorem. And there are, as you can see, there are several other such theorems. For example, Lenstra talks about cosecant values, but they are exceptions, actually. Okay, now for how many minutes? 1?
3 minutes, 40 seconds.
40 seconds. 42, 41. So for the tool that I need to introduce to prove this theorem is called Dirichlet character. And it's impossible to really do justice to this. But if you know something about group characters, these are basically group characters in Z mod n in the elements that are relatively prime to n. Okay? And now there's an important notion that I need in this whole proof is called an odd character, which says that the Dirichlet character takes -1 or -1. It's at least non-trivial. Now, expressed in the in this language, then what you're really looking at is what's called a cyclotomic extension. And if you can, you just trust me, this last equality is in fact true, that the cotangent can be expressed in some rational way of the primitive roots of unity of order n. And then they all belong to the the cyclotomic field, which is the rational field extended by the roots of unity of order n. And then there's this important tool. It's called the Leopold's character coordinates. This displayed equation defines it, where the G is what's called a Gauss sum, and where the sigma are the mappings that maps the primitive roots of unity of order n to the jth power, where J is a relatively prime element, and the Galois field is, in fact, of order phi of n that are relatively prime, the number of numbers that are relatively prime to n. So then you can easily derive a relationship from the summation of the chi of j, these are the characters, Dirichlet characters, with the quantity where the only difference from the left and right is t sub k versus t sub 1. Now, if you think about what a t sub k is that it's the cotangent on the kth multiple of the roots of unity on the primitive nth, k pi over n. And the Galois field will, in fact, change the t sub 1 to t sub k, and that's what the Galois field does for the primitive roots of unity. Okay, so the Gauss sum is known to be non-zero, so therefore you get the last equality. You can cancel the Gauss sum in this particular expression. And then basically the proof will proceed by arguing about certain cyclotomy in the nth primitive extension versus n prime extension, because if the cotangent of k pi over n is rationally related to cotangent of k prime pi over n prime, then they must be talking about the same cyclotomic extension field. And this is known to limit to the case of n either equal to n prime or equal to twice of n prime. And I think I need to skip this, but it's actually very important that there's a concept called a conductor of the Dirichlet character. And since we start with an odd Dirichlet character, the conductor is still odd. And then Gersmeyer actually proved such an equality on the Leopold's character coordinates. And then from this, let me just skip the rest, that one can analyze this by talking about what's called the generalized Bernoulli number. And this can derive that the only exception is when r equal to 3. And if you're interested, come talk to me or look at the paper. I'll stop here. Thank you. Oh, let me do a one-page advertisement. All the open problems are in this book, right? The book has just came out. This is on the classifications.
Okay, so maybe the next speaker can set up and we'll take a question or two.
Yes, Bobby.
Your trichotomy is for real values?
Yeah, yeah.
Do you know what the status is for complex values?
No, we don't. For the asymmetric, but for the symmetric, it is not. So, I mean, this book will sort of gives a general flavor of what is known, and lots of it is known for the spin systems and very precise characterizations. And the theme is basically that it's either in polynomial time or sharply hard in general, but tractable over planar, or it's even hard for planar. And the middle class is always solvable by the Castellan's algorithm via the reduction to the match gates. And I would expect for the complex case, it's also true.